Thank you, Joel, for accepting our invitation. As a quick introduction, Professor Seiko graduated PhD from University of London at the Institute of Cancer Research at the Royal Marsden. And then he became an assistant professor of radiation oncology at Harvard Medical School in Boston, as well working at MGH. And then he's come back to Europe, which is very good for us. And he's working at DKFZ, where he's heading a new group dedicated to ion beam research with looking at imaging, mechanism of radiation triggered DNA damage. And he is also the chair of the medical physics department of physics and astronomy at Heidelberg. So Joe, the floor is yours. Thank you very much.
Thank you very much, Manjit, for the invitation. And good morning, everyone. I hope it is morning for most people. And I will be talking about treatment planning. So if you do have any questions, please write them in the chat and I will try to address them at the end when possible, okay? I am especially in debt to Nicholas Wahl, who provided many of the slides, so I've acknowledged him clearly in their presentation. Okay, so radiotherapy has many components. It's like a chain with a lot of pieces that have to work well together. And if there is any failure in one of the pieces, then it's a problem. And they include things like patient fixation, imaging, identification and delineation of your cancer, treatment planning, verification and QA, patient positioning, and irradiation. I'm sure many of these have been dealt with already in the course. I'm going to focus on one of them, which is the treatment planning one here. All right. So a lot of this information can be obtained from the Wolfgang Schlegel book that was published many years ago. All right. So what is a treatment plan? What? Well, the treatment plan must fulfill clinical requirements, and this is what the clinician prescribes. So remember that when you do treatment planning for radiotherapy, it is the clinician that defines what your target is, what the dose are, what the constraints for the organs. This is ultimately his decision. You cannot do that. That's not the physicist's responsibility. Then the treatment planning part, the complexity of the algorithm requires many things, and one of them is to understand biological processes, and we try to develop models to mimic these biological processes. So the models that go in treatment planning systems sometimes include these biological processes. And of course, we try to understand how these biological processes, which are induced by chemical or physical reactions, how we can model them. So remember that the treatment planning system is a form of a model, a simplified model of your patient and the physics interactions of the particles in the patient. So how do we do that? Well, we do that with numerical simulations where we perform those calculations, and in many cases, we do optimizations of the beam components, of the beam intensity and the beam angles, and many things. Okay, so it is a pretty complex problem, and in many cases requires what is called an inverse problem. So you start from the patient and you work backwards until you reach the beam and you generate optimal intensity so that you can deliver that. So there is the so-called forward planning approach and the inverse planning approach. I will discuss both of them so that you can understand what it is, the difference between the forward planning and the inverse planning. All right, so imaging is one of the components that's really critical for us. We need to see what we're doing. And I wanted to put this picture of the first images, which are a simple 2D image of the hand of the wife of Röntgen. So you see the hand here, it's a simple radiograph. It has no volumetric information. It's just a simple planar image of a hand with a ring, right? So this is what we used to do for treatment planning up until the early 1970s. And then the discovery of the CT catapulted radiotherapy into 3D domain. So in a CT image, you build a 3D image of the patient by taking multiple slices of that patient. So it can be either multiple slices added together, or you do a helical image and you build a whole 3D image of the patient. So 3D X-ray therapy has revolutionized radiotherapy since early or mid 1970s up until now. So here's an example of a CT scan of a patient at different levels of the head. So this is the upper part of the head in the eye level, where you can still see some of the nasal cavity. This is a little lower. You see the nasal cavity here with the sinus. And here you see the base of the skull, almost the base of the skull here, and you see the brain with the teeth, right? So these are different slices, what we call axial slices, at different heights of the brain. So if you look at me, they're more or less one height here, one height there, and one further down, right? So these are axial slices. So basically a slice like this. This is an axial slice. You can also try to acquire different directions. So it has your axial or transverse slice, but you can also take a sagittal slice where you look from back to front, right? So it has your nasal cavity with your sinus and your throat. It has your skull with the base of skull down here, and you see the spinal cord here. And this is what is called a frontal or a coronal slice, where your image directly slices like this. So the image reconstruction allows you to build all directions of imaging. So the CT has extreme power that you can build this in full 3D. So if you put all of these three things together, you have a full 3-dimensional image of your patient on which you can do dose calculation. Another thing that is really important that the doctor has to do, it's his responsibility, is to define the organs. So he has to define the so-called volumes of interest, and that are usually the organs of interest, the healthy organs. So here are 2 eyes. The left eye on the right and the right eye here. Then you have the optic nerves, which connect the eye to the chiasm, and you also have the brain stem here. And in this case, there is a tumor identified by the doctor, which is this pink region here. And you always have to define the outer region for your patient. So the outer region is the so-called limit of your dose calculation grid. So the outer region is the head contour, and you see all these different regions. These have to be identified by the doctor. The doctor has to define the so-called volumes of interest from the healthy organs to the cancer itself. Okay, so here's an example of a very simple phantom that does not represent any patient, and the tumor is the red region. And for example, we have an organ at risk, this green ring here, that is in the center of this cavity, right? So you have a U-shaped tumor with a green healthy organ that you want to avoid. The ideal distribution that we would love to have is all the radiation covering the red, of course, and no radiation covering the green. This is not possible, of course, but this would be the ideal distribution. So how do we do planning and delivery? We use radiation beams, and the most common radiation beam at the moment, so 99% of all therapy out there is either done with photons or electron beams. So in the case of the photon beams, they treat around 80% of all patients, and the depth dose of a photon beam is given here. So you have the depth information on the horizontal axis, and you have the dose information on the vertical axis. And in this case, it's normalized to the max dose, which is here around 2 centimeters, right? And the depth dose for photon beams have a very shallow buildup of 1 to 2 centimeters, and then they have a very slow fall off, exponential fall off. So this is your radiation beam, and this goes on for as many centimeters as possible. So this is the photon beam, and then when we want to shape the beam to give any type of organ, we use what is called collimators. The most common collimator now in radiotherapy is multi-leaf collimator. So here you see the multi-leaf collimator with all the leaves that we can shape any geometry in one plane. Okay, so here's the example of one single beam coming in from the top, right? And you remember that there was a buildup and then a hotspot area just a few centimeters off the skin. So you see one beam coming in, you have the hot area here, and you have the fall off that gets colder and colder. So you see with one beam, it's not possible to cover very well the tumor while sparing the organ. So both of them get very high doses. So the trick is usually to add many directions. So as we add in directions, we build a dose distribution that covers the tumor, all right? So in this case, there is one limit to the problem, is that we are always delivering a uniform intensity of the beam. So in all these directions, we deliver a uniform intensity, right? So here's another uniform intensity. And as you see, this uniform intensity creates more or less a shape that is more or less the number of beams, right? So in this case, we have 7 beams. So you have a heptagon shape. So this is usually the limiting problem of forward direction planning, because you don't modulate the intensity, you deliver more or less homogeneous, and you cannot control the organ at risk dose, right? So you lose control for this organ here in yellow. So the question has always been, can we do better? Can we spare the organ at risk that's in the U cavity to radiation dose? So there is a concept that was developed in the 80s called the beamlet approach. And the beamlet approach means we break down the beam into tiny little beamlets, right? And they are tiny little depth doses like this, and they are usually very small. They can be sometimes 2 by 2 millimeter or sometimes 1 by 1 millimeter, but they're usually in that. And the beamlet is the same as the normal depth dose. For photons, it's just a very narrow beam. So he has one beamlet, for example, and you can add many beamlets to produce your whole beam, right? So the summation of each beam of multiple beamlets gives you a normal beam, right? So what is the advantage of the beamlets? Now we can compute those calculations for tiny little beamlets all together. So we can do what is called pencil beam planning through an algorithm, or we can even generate the beamlets through Monte Carlo, although this is extremely slow, and so there are various variance reduction techniques to do this faster. Right, so the key point with the beamlets is we have power to simulate and modulate our beam intensity. So remember, before I had a uniform intensity coming in. With the power of the beamlets, I can change this intensity to have any type of intensity that is needed. So I could change intensities to be like this. So like this, I have a variable intensity, or the previous one, I have a uniform intensity. So adding up these beamlets, I can produce any shape of beam, and I could even control it such that I can put more dose to the edges and less dose to the middle, protecting the organ from radiation, right? So usually you have a number of 100 to 1,000 beamlets, sometimes even more per field. So if you have many fields, you have sometimes in the order of 60, 70,000 variables that you have to optimize for. And this requires computational tools that are capable to do that. So here's the ideal distribution, and this is what you would get to building a system that can do that. So you want to build a dose distribution. So D star represents your ideal dose distribution that you convert into a vector with the number of voxels in this volume. You will then have a number of beamlets that you define, which is usually J, okay? And together, the reaction of the two of them produces a matrix that gives you the power to control the beam intensity. So here's the dose. You influence the J beamlets with the W, so you have this fluence weighted factor, the W that allows you to affect the beamlet. So this is the beamlet, and this is the dose. And so you have a matrix that converts beam information into dose information. So this is, and that matrix is your D. Usually it's called D or Dij, and that allows you to convert beam intensity into dose information. So I will repeat this formula a few times during the presentation, so you'll get to see it at work. All right, so what we need to do when we do radiotherapy is find the right W's. So here it is again. The solution has to be extended with a small epsilon that allows you to optimize this problem. And what we want to optimize in radiotherapy is W, right? We want to find the optimal W's that produce the correct dose distribution that we need. So what we do is we produce a small epsilon and we optimize that. So usually the problems are set up in a quadratic fashion. So here you have a quadratic function where you have dW minus D star squared. And so you're going to optimize this. You're going to minimize this for many voxels. So remember that your patient has many voxels. They can have in the order of 100,000 to a few million voxels, and you're going to minimize this. And the reason that we use a quadratic function is because quadratic functions have minimums. So you're somewhere up here, and you want to go down that way to that minimum. So you have to guarantee that there is a minimum. So you need a quadratic function to do that. And what you do is you're going to minimize this quadratic function so you obtain the optimal W. So how do you do that? Here's a simple example of your starting point where you have two weights, W1, W2, and you have a starting point somewhere. And your first step is always to start the whole optimization process. So you have to have an initial solution. You have to have an objective function, which is a quadratic objective function. And then you need to pick the gradient. And the gradient is highly critical how you pick that. Remember that you have a gradient where you're falling from some point and you want to go that way. So you have to usually do it mathematically. So you pick a gradient and you build a gradient, a local gradient. That's what you do. So that's what the definition is. The gradient says go downhill. And then you do a search of direction, and usually the search of direction is where it's going downhill, and you also have to identify the step length. So the step length can be very small or can be very big. You can take a very big step like that. So different steps means your algorithm runs faster or slower. Here's an example of a very big step from W0 to W1. You can then have another W step, and you keep going, and you move towards that minimum. Okay. And sometimes the min has some kind of constraints saying that you cannot cross this boundary, for example. And sometimes that means that you have to stop at a point which is above this constraint. So here, for example, different constraints are applied, and now you see you cannot reach this point, so you reach the point that is closest and positive. Okay, so it is a pretty complicated process, and the solution to this process usually requires different algorithms, and the most efficient one is called the Quasi-Newton method, but there are a variety of other ones that are implemented, like the conjugate gradient, and that one is usually what's implemented in many of the algorithms. Okay, so here's an example of the forward planning, and I'm gonna just overlap the intensity modulator. Remember that the forward planning, I had a hot region for the organ. If I do intensity modulated, I can literally remove the dose from the organ. And that's achieved by modulating the intensity of each beam. So the beams now have intensity that looks something like this. They're no longer uniforms, but they're all variable intensity. And I can control the dose very well with the IMRT by reducing the dose to the organ. So let's do it. Let's move now into hadrons and ions. The idea is the same. Before we start with intensity modulated particle therapy, I want to just mention the old style of planning. And the old style of planning used to use passive scattering. And the passive scattering, you have a collimator and a compensator. And these two things combined allow you to control very well the distal part of your depth dose. So this distal part was really well controlled, but you don't control the proximal part. So you see this shape of dose is basically a copy of that one. Sorry, it goes like that. And that's missing it, because now this is where you want it to be, and you're out here, and you have a hot area here, and of course you have a hot area here. So this is the old style passive scattering. You get some control of the beam, but it's not optimal. The new approach, which is based in intensity modulated, allows you to control both sides, and you don't need a collimator anymore. You do need scanning magnets, but you don't need a collimator. So the way to do it is you produce natural beamlets by changing their energy and by using scanning magnets to scan across the patient, right? And you use the power of the Bragg peak to irradiate any region in the patient. A lot of the big advantages of these pencil beams is they can very easily be modeled with deterministic models or even with Monte Carlo. All right, let me just show you how it is. Here's an example of a patient. He has a beamlet for particle coming in on one edge, right? And you can have another one coming in at the depth part. So you see you have the control both in the proximal part and in the distal part. So this is the thing that allows you with pencil beam scanning, for example, to do that. So you can you can produce any shape now of dose distribution with pencil beam scanning. Here's an example of a tumor that's fully irradiated with full control in all points. So here is how it works. For example, for the phantom again, you have your pencil beam coming in here. You can have another pencil beam there, another one there, and another one there. And like this, you can control the whole distribution to produce a shape with just one beam. You no longer need 5, 6, 7 photon beams. You can just do it with one particle beam. And notice that the dose distribution in the organ is also extremely low compared to the photons. So you can bring this dose distribution almost close to 0. So that's usually the great power of intensity modulated proton therapy or intensity modulated particle therapy. It's the ability to control the dose with very few beams. Okay, so let's have a look at the dose matrix again. So now in the dose matrix, you have a pencil beam for each point. So now you have one pencil beam for one depth, another pencil beam for another depth. And you see that all these points represent one depth of a Bragg peak. So one Bragg peak, another Bragg peak. And so now you have the control of all these pencil beams. And the good thing of the Bragg peak is that there is no dose after the beamlet. So here, there's no dose. So I'm putting crosses here to indicate there are absolutely no doses in these regions. But all you can control is these intensities of these points. So you have a big advantage relative to X-rays. You basically remove all the dose distribution on the exit side. So here's an example of how you would do it for the same phantom, the TGA 119 phantom. And you'll see, for example, has a starting point of a dose distribution. And as I start to add in more pencils, I produce the shape that I need, and soon it becomes relatively well conformed. And here's the example that's saying it's really close to what I need. So you see, I have a well conformed dose distribution to my tumor while sparing the organ here. So this is a big advantage for pencil beam. Particle pencil beam is really much better than photons. What about different ions? So now I want to talk a little bit about carbon, which is very different from protons. In the case of carbon, you could do exactly the same thing. You could also do dose modulation. But the problem with carbon is that they have a huge biological effect. So if you do dose modulation or biologically equivalent modulation, you have a completely different distribution. And that's because carbon has a very high RBE, between 2 and 3 for different patients. And that means that they change the biological impact in the function of depth. In the case of protons, the RBE for protons is 1.1, which is mostly used. That means there is no difference between biology and physical dose. So here's an example. For example, what happens if you optimize for biological dose? In the case of the right case, now I've optimized for the biological effect. I've maximized the carbon biological effect on the tumor. And if I just represent the dose on the left, you see it's completely different from the right. So when we do ions, we have to try to understand what is the RBE of the ion, and we have to use that information to optimize based on that. So that's what we call optimize for biology, or using RBE and instead of dose. Here's an example of all three systems put together for the liver. A biologically optimized dose distribution for photons, okay, a biologically optimized dose distribution for protons, and a biologically optimized distribution for carbon. So immediately you see one of the advantages, right? I need very little beams for protons and carbon to achieve the same distribution as photons. I do have some exit dose here in the carbons with some potential biological effects, but the dose is much lower in one beam than all these other beams put together, right? So we have a huge advantage in reducing the total dose to the remaining part of the body. So if this is my body that is outside the cancer, this part is getting significantly less dose than this region here with the photon beams. So you see the amount of dose given in the photons is usually 3 to 4 times higher than that of protons and carbon to the whole body. Okay, so then the question is, we produce these dose distributions, and how do we quantify them when we do the analysis of a plan? So here's a dose distribution for a photon beam. Now we have to analyze it. So we could do the evaluation on a 2D tomographic image. This is your 2D tomographic image. We could do dose statistics based on mean, maximum, min dose. We can also do dose analysis based on something called dose volume histograms. And the dose volume histograms convert very complicated 3D dose distributions into 2D displays, which is relatively easy. And finally, we can do also the biological analysis of the data. So NTCP or TCP are usually related to normal tissue complications or tumor control probability. Both of them are highly important parameters when analyzing plans. Okay, so here's the dose volume histogram. It's the most heavily used method to analyze data. And the dose volume histogram basically says that on the horizontal axis, I have the dose that I'm going to deliver to the organ, and I have a volume of the organ. So what, in this case, I have a dose volume histogram for a tumor. I want to guarantee that my treatment dose, this dose, reaches at least 95%. In this case, it's just represented as a number here, X%. But when we treat, we want to guarantee that the tumor is getting a minimum prescribed dose. So this is my prescription dose that the doctor says, I want to treat with this dose. So we call that the prescription dose. And this prescription dose has to reach at least 95% of the tumor. Right? So this has to be 95% of the tumor has to be covered by this prescription dose. And this is important to guarantee that nearly all the tumor is covered with the dose that you need. But you can also have a problem, like if this fall off of the dose distribution is not very sharp, right? And so what happens is I have a dose prescription, but somewhere in the tumor volume, I have a very hot area. Yeah, but notice that the dose here is one value, but I'm about 20% higher than. So ideally, we want very sharp fall-offs of the dose. We want to make this as step function as possible. So we're going to go all the way here and go like that. So that's the difference between ideal dose distribution and reality. We've tried to push this shape as close as possible to the dose prescription. Okay, so another way to analyze this was biological parameters. Like I said, the TCP represents the tumor. This is my tumor. Sorry for my handwriting on the computer. And this is the normal tissue. And usually there is a small offset between the two of them. And what we want to do is maximize the tumor control. So we want to be at a specific dose that has high tumor control and low toxicity. So here's a pretty good number. It's 60 gray. I have a big window of tumor control, close to 70, 80%. I could go even higher, where I get 90% tumor control, but now I start to have high levels of toxicity, and this is really a bad situation for the patient. I want my treatment to cure the patient, not to kill it. So you have to remember that there's always a balance between tumor control, TCP, and normal tissue complications. So we are usually in the domain of around 20 to 30% of toxicity levels. So sometimes the doctor will accept around 30, a little higher toxicity levels, but it's mostly in this domain here that you want to be. So you're somewhere here. Right. So the toxicity level plays a very big role because the person then has to survive the treatment. So there is a variety of models out there. The Lyman-Kutcher model was developed in the early 90s, and there's many others. And now there's also the most machine learning algorithms and AI-driven algorithms that develop models based on biological data. Okay, so the prescription can be more complex and abstract than the initial, but the prescription has to be converted into a math optimizing problem. So you have a prescription that's given you to the doctor. The physicist has to do this translation into an optimizing language, right? So that's the doctor that's defining what he wants to do, and you have to convert this into an optimization problem. So this is the tricky part, that the physicist comes in and does the work. So you have to define your optimization problem, and what are the parameters that allow you to do this. So you define the problem and all the stuff that goes into it, right? So the doctor can say, I want to keep my mean dose to the parotid low. So that's one option. So that means I want to introduce a constraint. This is usually called a constraint or an optimizer. So I want to define some kind of constraint or optimization focus, or I want to define a coverage for my tumor of around 60 gray, right? So this is sometimes called an objective. Okay, or you can have a mix of things. Do not exceed the dose 10 gray to the stem. It's another constraint. All right. So the doctor has to tell you what he wants, and you define then what is called a set of objectives and constraints, and this becomes your optimizing problem that you have to solve eventually. All right. So you can have an objective for the mean dose, for example. This is a simple definition of your mean dose. You can have an objective also for the tumor coverage. You can have also an objective for your brainstem, and you can also establish a variety of constraints, right? Different optimizers exist. You can have optimizers based on interior point method or sequential quadratic programming. Some of these are implemented in some of the standard algorithms. So research, for example, uses this sequential quadratic programming method. So for example, has an example of constraints and objectives. You see these little crosses here, these 3 crosses representing different constraints that you set. You want, for example, the brainstem, DVH constraints on the cerebellum and the parotid glands. So here's, for example, the parotid glands, which are these light blues. And then you have also the cerebellum, which is here, this green one. You set a constraint that you want 80% of the volume to receive less than 0.5 gray. So the curve has to go below this, right? Usually, and the same thing for the green line. You notice the green line is crossing this point because you set it that 40% of your cerebellum has to receive less than 0.5 gray. And you have another constraint where you set it at max dose for the brainstem. So here in the brainstem is set a max dose of 1 gray. These are examples that you can set as your constraints, okay? Okay, let's just come back. So here's, for example, the problem when you come to patients. So in patients, you don't just have one objective and one constraint, you really have many objectives and many constraints that to be formalized into a mathematical problem. So here's all these different objectives that you can set up. Square root deviation, under dosage, over dosage, mean dose, EUD is a biological parameter, equivalent uniform dose. You can also use min DVHs and max TSH. And these are the type of functions that you would use to define them as an objective. And then you also have to define your so-called constraints. And so in the case of the constraints, you have functions that look something like this: dmin minus k log, or dmax, or even cmin, and CUD, okay? And then under these cases, you can either objectively plan for CUD and DVH. So these are the stuff that you can implement. One of these functions you would use for your organs or for your tumor. So you see, it's not a straightforward thing, but there is extensive amount of experience now. And now there is a lot of understanding which functions do what. So the key point is that you always have to remember that there is always going to be a trade-off between sparing normal tissue, so toxicity, and tumor coverage. So you cannot achieve one and the other at the same time. The higher the dose to the tumor, the worse the toxicity. And so you have to establish the so-called trade-off between the two of them. And that's where the optimizer plays a major role. All right, so here's an example. I think, let me just quickly step into it. Sorry. So you see here, if I'm reducing the dose in this region, I'm putting it somewhere else, and it ends up being right in the back here. So by changing the dose distribution in one region, you're affecting another region. So here you see that the brainstem has got low dose, but you can change the dose to the mandibular, and you see how much the brainstem gets the dose. This is always the decision of the clinician. He has to define what's important and what's not important. So there are different ways to do this in a manual way with multi-criteria optimization, where now everything is done on what is called a Pareto surface, and you can optimize in a more efficient way all these organs at the same time. So we understand a little bit about inverse planning. I wanted just to bring up some of the problems that occur that also have to be accounted for when you do planning. So one of the things is uncertainties. Notice that the patient is supposed to be the same every day, but it's not. It's moving constantly. So you should be able to see that the patient is moving, right? And moving can be just from setup position or can also be just from breathing. So here's the patient breathing, and the motion anatomy, the anatomy and the motion that is produced can produce a significant change in the dose distribution that you deliver. So we have to deal with these uncertainties, and what physicists do is that they expand the margin. So the doctor is responsible for defining always the gross tumor and the clinical target. This is the clinician responsibility. The doctor has to do this. And the physicist is responsible for adding this additional margin to account for uncertainty. This is the physics responsibility that needs to add the additional margin. So I wanted to also mention one thing that is really important in particles, which is range uncertainties. And range uncertainties affect the position of the Bragg peak when we deliver. And what we would love to do is to have full control of the Bragg peak. So we would like to deliver the dose to this clinical target without affecting doses to the organ. But because of range uncertainties, we always have to expand the margin of the CTV to produce a so-called planning target volume, which is the red. And usually by doing that, we immediately put the extra volume into the organ. And this would guarantee that we have the correct coverage of the CTV, but we are voluntarily giving maximum dose to the organ, which is a terrible thing. So here's an example of the impact. You have a tumor sitting right next to the brainstem. When I expand the PTV, I get extensive dose given to the brainstem. And keep in mind, brainstem is one of the most radius sensitive organs in the brain. So there are a variety of range margin recipe in use in the US. These are all of them. And what happens is as you get deeper and deeper, the margin that you add increases. So for example, at 10 centimeters, the margin is roughly 5 millimeters. But at 20 centimeters now, that's practically 9 to 10 millimeters. So the margin that you add changes with the depth of the Bragg peak. So you see it's smaller in the proximal side and it's bigger in the distal side. And that's got to do with the uncertainty. It's cumulative with depth. Now, the funny thing is that the majority of the cancers that we treat with particles are deep, right? They are usually 80 to 90% of them are in the 10 centimeters of deep. And this is where you have these margins of between 5 to 10 millimeters extra. And so we're giving a lot of radiation dose to a variety of organs. So here, for example, in green is your abdominal tumors. In red are your thoracic or lung tumors. In blue is head and neck patients. And so you see that the variety of tumors increases and the majority of them are relatively deep. So we have a variety of way of constructing margins from CTV to PTV. The most well-known is the one from Marcel van Herk's formula that was developed, proposed in 2000, which combines systematic errors with random errors, okay? And like this allows us to expand the two of them based combining them. So expansion margin means we are going to be robust to the motion of daily variations and systematic errors that occur. So notice that this hot area is covering constantly the tumor, even though the tumor is moving inside the hot area. And the same thing here. Notice that the hot area is always covering the blue. It doesn't matter how much the blue works. This means our system is robust to uncertainties. And if we also have biological uncertainties, that's always a problem too. We also have to be able to model that. Oh, sorry. All right. So what we usually say is we want to make our system robust to uncertainties, right? And we add a margin that makes it robust to that. So we define usually that problem as minimize the worst case scenario, and we account for that in the way we do the treatment planning. So I think I have an example here. Here's the conventional treatment, which is larger, and here's the SFUD treatment, which is also larger. But if we develop an optimization problem and we make the whole problem robust to all these type of uncertainties, we see that the hot area is smaller than the others. The red area is smaller, and it covers the blue all the time. This blue tumor area is constantly covered for all possible shifts in my variations. So robust uncertainty gives you a very good power of controlling how to include uncertainties into treatment planning. All right, so to finish, you've learned a lot about treatment planning and how it works. You've also learned about several things from the biology to the importance of objectives and constraints for organs. You have to approach the problem as an inverse problem, so it becomes really heavy in mathematics. You have to understand how to do that. But it's something, the good thing is once you get a lot of practice with it, it becomes relatively easy to do. But you do have to approach the problem from an optimization perspective. Multi-criteria has changed the face of radiotherapy in the last 10 years. It's allowed us to really modulate the trade-off between organs and tumor. And this has made treatment planning a lot more efficient and transferred the responsibilities directly to the doctor when we do the treatment planning. And remember that the ion therapy has a huge advantage from the biology perspective, but we need to be able to account for uncertainties, and that's why we need the robustness when we do treatment planning. And I think that's the last one.
Thank you, Gerald, for a wonderful lecture and walking us through all the challenges, but also where medical physics ends and clinical people have to take responsibility, which is always a challenge, as you know, in these collaborations. Anyway, I'm going to pass over to the students for the discussion session. Please. Go ahead.
Thanks, Madrid. So as always, can anyone with any questions, stick your hand up and let us know. Okay, so we've got a question from Kristaps to start off with.
Thank you for the presentation. Just two interrelated questions with the range uncertainties. Do the range uncertainties only depend on the depth, or is the range uncertainty recipe we use a bit also depending on what kind of tissue are we going? Do we use the same margin if we go into lung or we go into some more solid matter? And also
range uncertainty recipes are broad.
Recipes change from single field to multi-field plans.
So range uncertainty recipes are broad, and they do the corrections based on depth of the Bragg peak, so water equivalent length. And that's because the range uncertainty affects everything that is downstream. So you could have a density variation very close to the skin, and that affects everything downstream. So the range uncertainty recipes are for that, to account for these uncertainties that occur all the way along the depth and affect the position of the Bragg peak.
And do we change a bit our recipes if we use more than one field?
So the range uncertainties depend on the depth of your pencil. So in one beam, you can have some shallower beams and some deeper beams, and you have to correct for that. So you would have a correction that is depth dependent per beam, okay? So you don't have just one correction for the whole beam. You have to know the depth of each ray. So you have to do the correction at the ray level. you produce an extra margin, and then you correct based on that.
Okay, thank you.
And we have another question from Roa.
Hello. Yeah, thank you for the presentation. It was very interesting. You mentioned that for multi-criteria optimization, there's been, you said the challenge is to handle the trade-off issue, basically. Could you maybe elaborate more on the Pareto surface that you mentioned?
So the Pareto surface is something I didn't mention because I thought it would be a bit complex. So when we have, oh, can I write here? For some reason I'm not, oh, all right. Can you see my screen?
Yes, we can see.
Yep.
Yes.
There is, let's say, somewhere up here in these two weights, right? So there is an optimal correlation between the two of them that is called the Pareto surface, right? So if you're these two weights, you can change the weights any way you want, okay? But they reach an optimal point where they cannot go any further anymore. So beyond this point, they cannot cross over. And on this Pareto surface, then you have a direct correlation between any weight, 1 and 2. And what you do is you, in this case, you can move up and down the Pareto surface to find the optimal, right. So for example, in this case, if I go up, I mean, weight 1 is more important. Let's say my weight 1 is the tumor, okay? So the doctor decides that the cancer is more important than the toxicity, right? And this one could be the organ, right? So I can run around randomly in this space without any strong correlation between the organs, but when I hit the Pareto surface, the correlation is strongest. And I can move up and down this Pareto surface. And that's what the doctor does now. He will have basically 2 bars where he says that this will be the tumor and this will be the organ. And he can move up and down this bar, defining. So there is some kind of slider, yeah, that he can move up and down, defining where. And this slider now is such that it's built to run along the optimal Pareto surface. This is the Pareto surface where the correlation is strongest between the two. And the doctor can then define. So if I go up in this one immediately follows. So they are highly correlated. So you see, so if I go up here, then this has to go that way, right? So if I'm here and I go up that way, then this one is going down. So this Pareto surface guarantees maximum correlation between the two of them, and they have to move in unison. So the doctor can then define where he wants to be. So sometimes the doctor wants to be here, okay? That's where the optimal is. But sometimes the doctor wants to be up here because he has a highly aggressive cancer and he's willing to give up on some of the toxicity. So the Pareto surface is the maximum correlation between your weights that allow you to then optimize. So this is just a simple example, but usually when we do planning for patients, we have about 5 to 10 weights. So it's a multi-dimensional problem that now is written usually sometimes as a star, if you have 5, for example, and you have now 5 weights, so you can move around here, up and down. They are highly correlated, these images. So it really depends how many organs and how many weights you have and how you play. So you move up and down the so-called Pareto surface and you achieve your optimal control. The good thing is, in order to calculate this Pareto surface, you just need to calculate a few plans, like 5 or 6 plans, and you can build a Pareto surface, and then it's really straightforward. Then the doctor just has to move around this Pareto surface to find his optimal point, okay?
Okay, we've got another question from Rita.
Can you hear me?
Yeah.
Yeah. Hi, João. I wanted to ask if, besides the planning target volume that you consider for the margins, do you do any more kind of treatment monitoring, like PET or something? Or
so there is a huge change in the last 10 years where we do what is called adaptive radiotherapy, where you can take images regularly during treatment and adapt if there is a change, okay?
So the CT?
With a CT or with an MRI, so you can do both. So MR Linux has been developed exactly for that, without daily adaptation if needed, okay? So there is a big problem there because every time you change the plan, you also have a problem that you have to have a new QA test of the plan. So So there is usually the big discussion at the moment, when do we do the QA of the new plan or when do we don't? So, but a daily adaptation allows you to change the daily dose to match the position for that day. That's what MR Linux are for, and also cone beam CT. So in-room cone beam CT was basically also for that. Allows you to position based on anatomy, but you can also check if the anatomy is wrong. And in some cases, you can change it. You can run a new CT and change it, yes.
Okay, thank you.
Okay, got any more questions? None. Oh, I think we do. Okay, so it's one from Julie.
Yes, can you hear me?
Yes.
Okay, I wanted to ask, yesterday we heard about the PATI concept where they would do partial tumor irradiations. For example, only irradiate the most hypoxic part. Is that common in the clinic already, or like, so do you use the PET?
It's called dose painting. So dose painting is a concept.
Yeah, that's what I mean. Yeah.
Yeah, dose painting is a concept that started in the early 2000s with a famous paper from Clifton Ling. He was at Memorial, and he basically said that if we have information like a PET or SPECT that tells us there's a hypoxic region, you can deliver a good amount of dose to the whole tumor, and then you can deliver a boost to your regions where there's hypoxic, right? And so dose painting has become pretty common. It varies, but it tends to, you do have boost regions. So you could treat the first 20 fractions with the whole volume, and then you boost in the final 10 fractions to a smaller region that you have identified through a PET or a SPECT, depending what, usually it's PET-oriented dose painting, okay? So dose painting is pretty common, yes. With carbon, it's slightly different. So instead of doing dose painting with the same photon beam, you could treat everything with protons and then boost the region with carbon. That's also what happens at the HIT a lot. So you treat the whole patient volume, the tumor volume with the protons for like 10 days or 3 weeks. And then you take a PET and you see where it's needed, and you boost that with carbon for 5 or 6 days, or for a few days.
Okay, that's interesting. And I guess the pencil beam is then also easier for.
So pencil beam is just a mathematical trick. It's nothing special. So from a mathematical trick, we can optimize anything. And in the case of carbon, when we deliver with pencil beams, yes, we have much better control of the shape and the depth. Yes. So that there's the pencil beam delivery and the pencil beam planning. So yes, from the delivery part, you have much better control in 3D.
Okay, thank you.
Okay, we've got another question from Maria, who's asking, in the clinic, how long does it take to have a complete plan ready to be delivered to the patient?
So the question is a bit tricky because there's before multi-criteria optimization and after criteria optimization. So before multi-criteria optimization, that can take a whole week to prepare this. Now with multi-criteria, it takes 2 days because all the responsibility of planning is taken out of the hands of the physicist, given straight to the doctor. And so the doctor has to come in and find the optimal plan in one shot, and then it's done. Before this whole process, it was an iterative process. The doctor would come to the physicist, and the physicist would then generate a plan, and then the physicist would contact the doctor, and the doctor would come back again. And the problem was exactly that. This whole circle would go over and over and over for days at a time, and this could take 5, 6, sometimes even longer than a week, right? With the multi-criteria optimization, the physicist basically doesn't calculate one plan at a time. He calculates 5 or 6 plans in one go, creates the Pareto curve, and allows the doctor then to navigate on it. And that basically means in one step, we get the full plan. So it takes 1 to 2 days. You always have to have a QA plan done before treatment. So that's at least 24 hours before you have to do a QA. So it's 2 days, 2 to 3 days now, with multi-criteria optimization working properly.
Okay, thanks very much. Another question from Christina.
Okay.
Yes, can you hear me?
Yep.
All right. So thank you for this lecture. I mean, this is what I'm a medical doctor and radiation oncology resident. So this is like my daily routine, and I always work with physics, and this is what we do. And can I have like, can you explain to us like a little bit more about re-irradiation? Like when you have to evaluate a plan of a patient that has been radiated like at least a year ago, and then like the disease presents again. So you have to do another plan, and how do you evaluate that?
So re-radiation is a tough thing because you also have to account for the time. So if you radiate a patient, say 5 years ago, and then you have a certain level of recovery from the tissue, you have to account for the dose that you gave to the tissue 5 years ago, and then you have to account for the recovery. And then if you irradiate the same tissue, you have to take into account that there was given some dose. So the way we used to do re-radiation is we would go unarchive the old plan, produce a dose distribution, multiply that by a factor, which is time dependent, like multiply by 10% or 20%, depending how long it was. And we make a new plan on this new corrected system with the knowledge of the dose. That usually depends on the clinician. He will say, right, 5 years ago, you include only 10% of the dose or 20% of the dose. If it was 1 year ago, then you include 50% of the dose. So you have to know more or less this time delay that is related to the recovery of the tissue, right? But that's usually something that you have to have both plans together. You have to have the old one plus the new one, and you have to add them up together. It's not perfectly linear, but it takes time. Yeah.
Okay, question from Habiba.
Yes, hi, thank you for the talk. I was wondering, did you have to change the way you optimize your plans before using MCO, or did you just keep on using the same optimization?
You use the same algorithms, you just have to build the alternative part of the multi-criteria. Means you have to build multiple optimal plans. So you build after them, and then you have to build the search engine for the MCO. So you have a search engine that will search along the Pareto curve. So ultimately, you're going to have a lot of plans, but you're not building random plans now. So you see, the problem is exactly that. Huh? You have to start somewhere and then find your Pareto curve and then build plans along the Pareto curve. So that's the tricky part. It's just designing the Pareto curve in the optimizer such that then you can, once you have the Pareto curve, you can build this method of sliders that allows you to navigate.
Okay, yeah, but I mean, did you keep on using the same objective and constraints you used to?
So yes, the functions are the same. It's just the search space changes.
Okay, great, thank you.
Okay, and we've got a question from Louisa concerning the uncertainties due to, for example, the breathing process. Are there attempts to create time-dependent treatment plans taking into account periodic body movements?
No, body movement is never periodic and definitely not reproducible. So it's really not possible to do tumor tracking. It was kind of idea proposed in the 90s, and kind of people in different centers try to investigate it, but tumor tracking is really not easy to do. In fact, it's not straightforward. So now what they do is either form of gating, or they create a large margin to account for motion, which is called the ITV, okay? The internal target volume is specifically designed to account for motion. Or if you have, for example, MR Linux, you might be able to target the moving region, but even then you don't target it by tracking and dosing. It's really not straightforward. So you try to control a region where it's going to be most of the time. So the motion is never periodic. It's got a sine wave, sine 4 wave distribution that looks something like this. And so because it spends most of the time in this region, which is the exhale, you gate your treatment to this region, which is the, so when you breathe, the most reproducible part of your breathing is your exhale. It's long and always ends up at the end. So you target the exhale phase when you treat for motion, but it's possible. So, yeah.
Okay, we've got a question from Lam who's asking, how about, so this deep-seated small tumor located in the brain, basically, is this an example of the more sort of challenging types of tumors?
No, in fact, for brain tumors, the small brain tumors, the best technology out there is called stereotactic radiosurgery, or SRS, because you can deliver extremely high doses to very small volumes and extremely well controlled. So you could use particles, but when they are small volumes somewhere in the brain, they tend to be SRS. And only you use IMPT or IMRT when the volume is not a ball, when it has the form of a U shape. Then it changes a little bit. But SRS has been shown to be the best for small tumor volumes in the brain.
Okay, so it would be quite challenging to do this with protons.
Yes,
okay,
for sure, but yes.
Okay, thank you. And we've got a question from Kristaps.
The question is about treatment imaging. Just
about
wondering
about what? Sorry, about
pre-treatment imaging.
Right.
The one that we use for planning. So what is the role, I don't know, currently or in the future of dual energy computed tomography in that compared to single?
So the role of dual energy is to provide you a better estimate of stopping power. So you need to make an estimate of your patient and convert that estimate into stopping power. Single energy has a big uncertainty because of the I value and other things that affect it. when you do dual energy, you have a much better estimate of the electron density and the I value together. So the error drops to around 1%. So it goes from 3.5% to 1%. So you have a factor 3 drop in the uncertainty of stopping power. Factor 3 to 5.
Good. Technically, if we would use dual energy CT, we could also a bit lower the range uncertainties that we use in planning.
See, it's for range uncertainty errors, only for range uncertainty, primarily dedicated to range uncertainty. It does also offer some better contouring, but it's primarily for range uncertainty, yes.
Okay, thank you.
And we've got another, I'm sorry, another question from Christina.
Maybe she's...
Or maybe her hand's still just up after the last one.
Okay.
Habiba, is your hand still up? Have you got another question?
Yeah, no, I still have another question, please. As a physicist who has experience in photon and protons, would you say that your planning techniques is the same in photons and protons, or?
So the optimizer, yes, the optimizer should not be a problem. The big difference is the delivery of the radiation that is very different. Right, okay. So the delivery becomes a critical component. When you finish the optimizer, you have to deliver it. So you have to pass it through a leaf sequencing algorithm for photons, or you have to pass it through a pencil beam scanning algorithm to produce the pencil beam. So the delivery method changes, and there is usually a bit tricky.
Okay, great, thank you.
I think that's almost all the questions from the students. I've got just one question that was asked by one of the students on the Google form at the start of the course, which was, where are we currently with the modeling of the effect of radiation in pediatric patients? So is this, which sort of stage is this taken into account? Is it taken into account in the treatment planning with extra weighting, or how is that how is it basically, how are pediatric patients treated differently at this stage?
So pediatric patients are given less dose. The dose prescription for most pediatrics depends on their age, right? So the younger patients have less dose, the older patients have much higher doses. And yes, the modeling is more subjective to experience in different clinics. So of course, there is a protocols for pediatric patients, which is universal, but mostly it's difficult to model pediatric growth because it changes from patient to patient. So what they do is they develop models which are age specific mostly.
Okay, thank you very much. I think we don't have any more additional questions. Obviously, if anyone's got any more questions, feel free to add that to the Slack chat. I'm sure there are going to be some more after this. It was a very interesting lecture, so thank you for that. Anyone else got anything to add? Manjit, I think, are we all?
Okay. So thanks, Cameron. Thanks to the students for your questions. And thank you, Joe, for a very interesting lecture. And the students sometimes are sending questions afterwards on the Slack channel. So if you don't mind, we will share them with you if some come up. Okay. So thanks again. And see you in the next session, I guess. Okay. So I think Andrea has